Hi, I'm Mirjam Lanzer, and I'm a research associate at the Department of Human Factors at Ulm University in Germany. Today, I want to present our paper, Interaction Effects of Pedestrian Behavior, Smartphone Distraction, and External Communication of Automated Vehicles on Crossing and Gaze Behavior. Automated vehicles are expected to bring advantages to various domains, for example, the environment and safety. In urban areas, up to 73% of analyzed pedestrian crashes would be avoidable with fully automated vehicles. They also bring new challenges as driver-pedestrian communication is no longer available. To solve this, external human-machine interfaces, or EHMIs, were proposed and evaluated. While some researchers argue that implicit communication, such as the vehicle's movement patterns or engine sounds, is sufficient, the majority of studies seem to find positive effects of EHMIs. Pedestrians feel safer to cross, trust the automated vehicle more, have a reduced cognitive load, and initiate their crossing sooner when automated vehicles are equipped with EHMIs. However, most of these studies were done in a simplified scenario with one attentive pedestrian and one automated vehicle. This is a logical first step when investigating a new technology, but traffic is a complex system where there are multiple influencing factors that interact with each other. From a large body of observational research, 38 factors were identified that influence pedestrians' crossing decisions, including characteristics of the pedestrian and the surrounding environment. The first relevant factor, as we just talked about, is the communication between pedestrian and automated vehicle. The second relevant factor for our study is the behavior of other pedestrians. Pedestrians are rarely alone on the street. Instead, they are accompanied or surrounded by other pedestrians. And the third relevant factor is the pedestrian's attention. Pedestrians often handle a secondary task in addition to crossing the street, such as using their smartphones. All these factors do not exist in isolation, but they interact with each other. So understanding how these factors interact with each other is particularly important as traffic is a complex system with practically no situation with only one influencing factor. So the main effects that were found so far cannot simply be transferred to more complex scenarios, as it seems unlikely that one factor is so strong that it has the same effect in every context. Regarding automated vehicles, it's important to understand under which circumstances EHMIs have an effect. So why did we choose these three factors? All of them either promote or hinder the intake of information that is necessary for the decision to cross the street. EHMIs in the presence of other pedestrians can provide cues to the pedestrians to help them correctly assess the criticality of the situation, make a crossing decision, and feel safe doing so. On the other hand, smartphone distraction interferes with and negatively influences these processes. There is, however, a research gap on how EHMIs interact with pedestrian factors. So far, EHMIs and smartphone distraction have not been studied together. No interaction effects were found between an infrastructural EHMI and a distraction task that was performed by pedestrians on a billboard. However, guidance given on a smartphone screen helped distracted pedestrians make successful crossing decisions in non-automated traffic. As for EHMIs in pedestrian groups, scalability of EHMIs is an emerging topic. Automated vehicles should provide clear and unambiguous communication when multiple pedestrians are present. So far, there are no studies that calculate or report any interaction effects between EHMIs and pedestrian groups. With our study, we wanted to close this research gap by investigating what interactions with each other the variables EHMIs of automated vehicles, a crossing pedestrian group, and smartphone distraction have on pedestrians' crossing behavior, gaze behavior, and subjective perception of the crossing. So we conducted an experiment in virtual reality with 115 participants with a 2x2x2 within design. The first factor was the EHMIs of the automated vehicles. They displayed the intention of the automated vehicle, so either driving or stopping, and were active or inactive. The second factor was smartphone distraction. This was implemented by a virtual smartphone on a handheld controller where participants continuously performed the NBAC task, a cognitive performance task. And the third factor was the presence of other pedestrians also crossing the street. A group of 3 simulated pedestrians was implemented that crossed the street shortly before the participant. We then measured the pedestrians' crossing behavior, their gaze behavior, and their performance in the smartphone task, as well as how they perceived the crossing in terms of workload, safety, and criticality. Due to time constraints, I will only present a summary of the key findings of our study. For further details, please refer to the paper. So when the pedestrians were attentive and not distracted by the smartphone, the EHMI had several positive effects. Pedestrians crossed faster, they perceived the situation as less critical, they had a lower mental demand and perceived effort, and a higher perceived safety. This is consistent with previous research that was conducted to date with attentive pedestrians. However, when pedestrians were distracted by the smartphone, the positive effects of the EHMI disappeared and no differences were found for these variables. As far as we know, this is the first study that demonstrates that the previously found positive main effects of the EHMIs when examined with attentive pedestrians do not apply for distracted pedestrians. This means that EHMIs seem to be less useful for pedestrians in more realistic scenarios. Possible explanations why the positive effects of EHMIs disappeared when pedestrians were distracted could be that either they did not perceive the EHMI altogether or had no capacity to process the provided information. The gaze data shows that distracted pedestrians did indeed look less often at traffic, but they looked proportionally longer at traffic when they were distracted and the EHMIs were active. This also provides a possible explanation why they made more errors in the smartphone task when the EHMIs were active. The EHMI drew more visual attention towards the vehicles as these are salient stimuli, so that participants spent less time on the smartphone and made more errors. This could be interpreted as either beneficial because the attention of pedestrians was focused more on traffic, but it could also be disadvantageous as it adds more visual load. The second possible explanation assumes that the EHMIs had no effect when pedestrians were distracted by the smartphone, as they did not have enough capacity to correctly perceive, understand, and interpret the additional EHMI information. Pedestrians indeed looked longer at traffic when the EHMIs were active and they were distracted, which could be an indication that they took longer to process the additional information provided by the EHMI. However, this is not reflected in their subjective assessment of mental demand. As the interaction effects with the crossing group suggest, distracted pedestrians might rely on more familiar cues like other crossing pedestrians compared to the external communication of automated vehicles when their cognitive resources are limited. The results show that the crossing group had several positive effects such as a higher perceived safety, a lower perceived criticality, mental demand, and effort when the pedestrians were distracted by the smartphone. No effects of the crossing group were found when the pedestrians were not distracted. This implies that the crossing group is not beneficial when pedestrians are attentive, as they presumably then do not need the additional crossing information provided by the group. When pedestrians are distracted, however, they benefited from other pedestrians crossing in front. This is also reflected in their gaze behavior, as they looked less at the stopping automated vehicle when the group of other pedestrians was crossing in front. A possible explanation is that following a group could be a way to compensate for the load that is induced by a distracting activity in a way that relying on the group's social information is a mechanism to spare one's own resources. In conclusion, we can say that interaction effects appear when pedestrian factors are included. While EHMIs have a number of positive effects in idealized crossing situations, they are less helpful in more complex scenarios. When pedestrians were distracted by a smartphone, they relied more on social cues provided by the crossing group than on technical cues provided by the EHMI. So how to proceed from here? The results of this study show that it is necessary to examine EHMI concepts in more complex and realistic crossing scenarios. We should also discuss under which circumstances EHMIs are beneficial and needed. And lastly, we might need to develop new concepts for the communication between pedestrians and automated vehicles, as the existing concepts do not seem to be universally applicable. Thank you very much for your attention. I'm happy to answer questions, so feel free to contact me or any of my co-authors.